requests, some people asked to look at acids and bases, and also some for electrochemistry. So we're going to do this first, and then we'll see what the time looks like if we go on to electricity today. Right. So we're starting off. So for some of you, it would have been a very fast week in which they did acids and bases, right? For some of you might even not have reached acids and bases yet. Can I just have a quick show of hands? Who did acids and bases? Right, so most of you, right. But there's a few for who is totally new, right. But the grade 11 acids and bases are not that much, right? In matric you go on, but if your basis in grade 11 is not right, then they have to reteach you a lot of things in matric, and they don't have the time in matric. So what we're going to do is today, I hope all of you received the notes, it's extra, on acids and bases. Right, now the very first thing with acids and bases is you have to know the names of the acids and bases. And not only that, you also have to know if they're strong or they're weak. Right. This is not something that you can look at the formula and know. You have to learn it. So this table and that table, you will have to learn by heart. Right. Now, most of you in grade 10 and grade 9 already learned the first three at least, and maybe even oxalic acid, right? So hydrochloric acid, sulfuric acid, nitric acid, that's old friends, right? And then we get to things like oxalic acid and acetic acid. That's maybe a little bit more new, right? But for our purposes, it's very important, right? We have to look at those, especially since oxalic acid is one that we have to use in the practical as well. Right. Now, if you look at oxalic acid, there you will see there's two different formulas, right? Now, sometimes you will see it written as the top one, right? And that's the one actually I prefer, that's the traditional one. And sometimes you will see it written in this way, right? Why do they do that? Now, if you look at oxalic acid, the acid is actually, well, when you get to matric, you will learn that the acid is like this. Next time this year, this time next year, you will be able to draw it, right? So you've got the two hydrogens on the opposite side, right? So it won't lose just one. Usually it loses two, but it's a weak acid, right? So you don't have to remember what it looks like, but it makes it easier to understand that two. Why just double two, right? Why just 2 times that? So you can't remove the 2 and just write COOH. It's not the same thing, right? You have to have the whole molecule, right? So it must be COOH 2. So it's twice that part of the molecule. Right, so why do they write it like this? Sometimes they write it like this because then it looks like sulfuric acid, right? And if it looks like sulfuric acid, then it's easier to write the equation. So you can write either, right? They will mark both, right? But I always tell my learners, you have to learn both. Because when you get into the exam and they wrote the equation, they could have chosen either one, right? So if you get there and they use this one and you learned only the top one, then you will be having problems, right? Or the other way around. So you have to learn both. So hydrochloric acid, easy. You've used that a lot of times. Sulfuric acid, right? Easy. Also a strong one. And then nitric acid, also a strong one. And then all the rest. Phosphoric acid, we don't use that much. But there you go. Those are the 4 strong ones. And all the rest will be weak. And even if they give you one that you haven't seen, one that's not on my table, you can usually expect it to be a weak one, right? So those 4, you must learn them by heart, they're strong. Any others, they will be weak. And we'll tell you why it's important to know weak or strong, right? So those are strong. Then carbonic acid, well, it comes from carbon dioxide that's dissolved, right? Carbonic acid, it's a weak acid. Oxalic acid, that's the one that's new to most of you, right? So pay special attention to that one, right? The oxalic acid, there you go. And then the last one, acetic acid, most of you saw that one. You sort of learned it by heart in grade 9 or 10, CH3COOH, right? Sort of like that and not understanding. Right, now the last two are different from the top ones. How does it differ? With all the top ones, the hydrogen is in front, right? And with these last two, you see the hydrogen there at the back, right? Now, the last two are organic acids. Now, in the beginning of grade 12, you will do organic chemistry. Then you'll understand more about organic. But just remember here, with these two, they're still acids. It's just that the hydrogen that they will give off is at the back, right? So that's your acids. Let's look at the bases. Now, the bases, strong ones. Which are strong ones? The first three, right? Sodium, potassium, lithium. What's the same for sodium, potassium, and lithium? Do you have your periodic tables? Just take them out and look at your periodic tables. What is the same for sodium, potassium, and lithium? Now, if you know your periodic tables by heart, you will know they are all in group 1, right? And I know you can't remember much about grade 10, but when you were in grade 10, you learned that group 1 ions always give salts that can dissolve, right? So it doesn't matter which salt, it will dissolve. So it will give off the OH minus, right? So in this, the first three being in group 1 will be the ones that dissociate easy, but we'll talk about dissociate when we get to that. Right, so those are strong. And then all the rest, they will count as weak. And we'll look and we'll talk about why we call them weak. Right, so this is the first thing. You just have to learn it by heart, right? There's no short way about it, right? If we can understand something, we prefer that, but this you have to learn, right? So then we go on. Now, if we look at the next part of that page, right? Reactions of acids. Now, that is actually grade 10 work, right? You even did it in grade 9. You repeated it in grade 10. So this should be old news, right? All the types of reactions that an acid can do. An acid and a reactive metal, salt and hydrogen gas, right? Acid and a base. Now, for a base, we're going to use the metal hydroxide, right? That will also give salt, but now we have water, right? Which is the most stable compound, H2 or H2O? Okay, how will I know? If you think about H2, do you know a lot of places that you have H2? Do you know a lot of H2O? Yes, we've got C's full of H2O, right? So there must be a reason why it prefers to be H2O rather than just H2, because it's more stable, right? It's more stable. So if it can form water, it will form water. If you look at the first one, there was no oxygen to bond with. That's why it didn't make water, right? It's just the metal bonding onto the negative side of the acid. If we go on, this one, now we have OH in the base, and that supplies the oxygen. So now we can make water. Right, next one, acid and metal oxide. Right, same thing, salt, and since there's oxygen available, we can make water. Right, and then the very last one, acid and the metal carbonate. Carbonate, right, CO3. What's the charge of that ion? -2, right. So what happens is it's actually an ion exchange reaction, right? An ion exchange reaction. So you get the zinc chloride, that's what we expected, and you also get the H and the CO3. And if you think about it, H2CO3, right? If you bonded those ions, they would give H2CO3. But H2CO3 is less stable than the separate H2 and CO2. So the moment that it forms, it immediately breaks up into CO2 and H2O because it's more stable, right? And you know it, right? C is full of water, carbon dioxide, right? There's a lot of that. Why? Because it's stable, it's low energy. So it prefers to be in that. But this was grade 10 work, right? So everyone happy with grade 10, we hope. Right, let's just go down here and just do one exercise to see if you are fully covered in this one. Let's see. Write 4 balanced equations to show how magnesium chloride can be prepared. Right. We want to prepare magnesium chloride. What does magnesium chloride look like? Well, magnesium being 2+ and chloride being negative, we need to make MgCl2, right? And now I want you to write 4 reactions that will give magnesium chloride as your product. Sorry, magnesium chloride, magnesium chloride. 4 reactions that will end up giving you magnesium chloride. And that is from the appropriate acid. Now, if I want to make a chloride salt, what would be the appropriate acid? Yes, I can hear. HCl, right? You will start with hydrogen chloride because you need the chloride. So if your acid has got the chloride and it does an ion exchange, then that chloride will end up in your salt, right? So we need to have hydrogen chloride for all 4 my reactions. But how can I add the magnesium? Well, go back to your reactions, right? You could have added it as a metal on its own, right? So that's the first one. Let's HCl and magnesium on its own, right? What do we get products? Well, if it's acid and metal, you get the salt, all right? We already have that one. And what should be the other product? Hydrogen gas, right? Plus H2, and always write gas, right? Never mind about the other things. You can write solution, solid solution, right? But this one, very important, gas, because next year when we get to rates of reaction, you need to know this is a gas because it tells you how you can work it out. Right, next one. How can I also add the magnesium? Go back here. We can add an acid and a metal hydroxide, right? A base. And that we call neutralization. So this is a neutralization reaction, right? And you can also remember it's always exothermic. So what will happen to the temperature of the beaker? Yeah, it should rise. Exothermic exits energy, right? So if you look at this one, you can add magnesium as the hydroxide. What does magnesium hydroxide look like? Yes, magnesium being 2+, you need 2 hydroxide ions with that one, right? And then what should the other product be? Well, if you add an acid and a base, you get salt and water, right? So the other one is water. And now all we need to do is we need to balance this one. Let's do this by inspection. 1 hydrogen, 2 hydrogen. So you need a 2 over here, right? 2 hydrogen, 2 hydrogen. 2 chloride, 2 chloride. 1 magnesium, 1 magnesium. Okay, but there's 2 hydrogen, there's another 2. Okay. So I need a 2 over here as well. Right. Hydrogen, 2, 4, 2, 4. 2 chloride, 2 chloride. 1 magnesium, 1 magnesium. 2 oxygen, 2 oxygen. Right. Everyone happy? Right, let's move on. How can I also add the magnesium? Let's go back. We already did the metal, we did the hydroxide. I could have added it as a metal oxide. So let's put it in as a metal oxide. 2 plus 2 minus, just like that. And then what should the other product be? Now let's go back. Acid and metal oxide. Now I should end up with the salt and water once again. Right, so it should be water. Right. And now to balance, 1 hydrogen, 2 hydrogen. Okay, put a 2 in here. 2 hydrogen, 2 hydrogen, 2 chloride, 2 chloride, 1 magnesium, 1 magnesium, 1 oxygen, 1 oxygen. Perfect. Right. And now how can we put it in? Last one, acid and metal carbonate. So now we've already got the acid. Metal carbonate, magnesium, 2+. Carbonate, 2-. Nice. So it's just magnesium carbonate. And then if we put that together, it gets magnesium chloride. And what should we get as another product? Let's go back. Right? You can make H2CO3 and it will immediately split up, right? So I will have H2O and I will have CO2 in the gas form, right? 4 possible reactions, right? Now, especially the second one is very important. When you get to matric, you're going to do a lot of titrations and you're going to do things like that we call hydrolysis, when you have to know what acid and what base was used to make the salt. So you have to be able to go back, right? Everyone happy? Right, so we finished with grade 10. We can move on. Thanks. Right, let's move on. Next page. Something that you learn in grade 11, right? If you get a reaction, right, an acid-base reaction, and we're still going to talk about how to write it. If you get an acid-base reaction, if you look at this one, NH3 on this side, right, and NH4 plus on that side, what happened from here to there? It gained an H plus, right? It gained an H plus. And if you gain an H plus, right, this one is a base, right? Because a base is something that gives off an H plus, right? It donates the proton. We'll get to that soon, but look at those two. They just differ with one H plus, and therefore we call them a conjugated pair, right? They just differ with one H plus. What about the other twos? When you look at water and you look at OH minus, what's the difference between them? One H plus, right? So they are a conjugated pair, right? Conjugated pair. So what is an acid? Acid is something that can donate an H plus, right? What is a base? That is something that can receive an H plus, right? And in a pair, if you have this one and it's the base, in the forward reaction, it means it will receive an H in the forward reaction. Is that right? Now look at the NH4 and look at the reverse reaction happening from the back to the front. If you start with NH4 and you end up with NH3, what happened to the NH4? Yes, it gave off an H plus. So this one is actually an acid, right? So if you want to look at NH3, you have to look in the forward direction and see it's receiving an H plus, right? If you look at NH4, you're looking at the reverse reaction and it's giving off an H plus. So now it's an acid, right? And they're a pair, a base and it's conjugated acid, right? And also for water, water in the forward reaction donates an H plus. That makes it an acid, right? If you look at OH minus in the reverse reaction, what happens? It gains an OH plus, right? So therefore it's a base, right? And a base and they two together differ just with one H plus. So they're a conjugated pair as well. So they're going to ask you conjugated pairs. So let's look at this one. I ask you to write down the conjugated base for the following acid. Write down the base for the following acid. So what do they give you? They give you the acid, right? And they're asking for the base. So what should the acid do? It should give off an H plus, right? So if this one gives off an H plus, it will end up NH3. If this one gives off an H plus, where are we ending? SO4, but now -2, right? Very important. We're not just giving off an H. We're giving off H plus, right? And if you really put away a plus, then this will become 2 minus, right? What about the last one? If we give off an H plus, you will end up with OH minus, right? OH minus. Right, the next question is the other way around. Now I am asking you, write down the conjugated acid of the following base. So what are they giving us? They're giving us bases, right? So what should the base do? It should accept an H plus. So this one will become, yes, nice, H3PO4, right? So it added a hydrogen, and because it's plus, you will no longer have that minus, right? How about the next one, OH minus? If I give that a H plus, it will be H2O. And that one? Yes, H3O plus. And that one is special. It's got a name. What's the name of that one? Hydronium ion, right? It's a hydronium ion. And that's very important, because if there's a hydronium ion in the solution, then the solution is acidic, right? And actually, you are adapted to identify hydronium ions, right? Which part of you were made specially to identify, well, not specially, but made to identify hydronium ions? Your tongue, right? The moment that you taste something, you say, this is acidic, right? How did you know that? Because the H3O plus, the hydronium ion, went and it was registered on the receptors, right? And that's how you knew it was acidic. So you can immediately tell something is acidic because it's got H3O plus. And how do you know? Because, you can register H3O plus, right? So if something is very acidic, what does it tell you? There's a lot of H3O plus hitting your tongue and registering, right? So let's go on. Next one. Now something from moles that we have to use in acids and bases. Concentration. This is not a new one, hey? We did that on Tuesday, right? So this is not new. Something that is new is dilutions, right? Sometimes you've got a very concentrated solution and you want to add water, right? So the important thing is adding water, right? You get a dilution when you add H2O. Now, why is that so important? Because with acids, we are going to add a lot of different things to acids, right? So, for instance, we added reactive metal, we added metal hydroxides, right? But sometimes we are going to add water, right? And if you just add water to an already acidic solution, you're just diluting it, right? There's no other reaction, it's just dilution. So let's look at this one. What do you do when you dilute something? You take a small volume of a very concentrated one, right? A small volume of a very concentrated solution. Now, if you look at C equals N over V, you will get the moles of acid in that one by C times V. Is that right? Okay. So in this one, I have C times V moles of acid. What do I add to that? If you dilute, what do you add? Just water. So how will the moles of acid in the little bit that you threw into the beaker compare with the moles afterwards? They should be the same. The moles before should be equal to the moles afterwards, right? Because what do I add? I only add water, so I'm not adding moles of acid, right? The moles of acid should be the same, right? But then for moles, we had concentration times volume, right? Concentration times volume, right? So on this side, it is my old solution, right? So you take the old volume and the old concentration. On this side, it is the new concentration and the new volume. But now you have to be very careful. What goes wrong with this? This one, right? This one. The piece of the volume of the water added is not my new volume. The new volume is the total new volume, right? Okay, so that's actually very easy, but you have to be able to do that because sometimes you have to do that and then you have to go on with the metric type of questions, right? So all of you should be able to do this, but let's do the first one together, right? 25 milliliters of water. Now a milliliter is just a cubed centimeter, right? 25 cubed centimeters of water is added to 75 cubed centimeters of water, of sulfuric acid with a concentration of 0.13. And now they ask us, calculate the concentration of the diluted solution, right? Now, the moment that you see that it is dilution, we're going with C1V1 equals C2V2. Right. Now, what unit do I usually use for volume? Cube decimeters, right. But there's a trick that you can learn. If you look at this one, can you see V being on both sides? Right? So now you don't need to work in cube decimeters. Cube centimeters would be fine because you are working with the same unit on both sides, right? So if you are afraid you're going to forget when to use and when not to use, right? Always use cube decimeters. But in this one, it's not necessary because it's on both sides, right? Let's go back to the equations. In that one, can I use cube centimeters? No, there's only one V, right? So it should be in cube decimeters. But if it's on both sides, then it doesn't matter, right? Just don't use cube centimeters on one side and cube decimeters on the other. Use the same one, right? Okay, so let's go on with this one. We started off with a concentration of 0.13, and we started off with 75 cube centimeters, right? Or you can write 75 times 10 to the minus 3 if you prefer. Equal to, we're looking for the concentration afterwards, right? And now we get to that new volume 1, right? What is the new volume? The new volume is both together, right? So now we are 100 cube centimeters, right? If you wanted to do it cube decimeters, you would have put minus times minus 10 to the minus 3 times 10 to the minus 3, and it would have cancelled out, right? Okay, and then you can just work it out. Right, and if I remember correctly, it was something like 9,72 times 10 to the minus 2. Do I remember correct? Right, okay, 10 to the minus 2. And the unit for concentration being mole per cubed decimeters, right. That centimeters and that centimeters cancelled out. That one was cube decimeters, so this one should be cube decimeters as well. Right. Now there's two more, right? And I think you can now do those two for practice. Paper. Sorry. Mm-hmm. It's fine. It's fine. Let me just see. Okay, this 140. Okay. What's it? 384. I think so. Yes, I think so. Right, so the first one was what we did yesterday, or the day before, m times v. If you preferred, you could have done it in two different equations, n equals m over m. That was fine if you did the one and then the other, but it was easier if you just put it in. They ask what mass, so they're looking for m, must be dissolved in 240 cubic decimeters, so you've got a volume of 0.24, right? To give a 0.04. Right, and now we're looking for big M. Periodic table, right? And I saw everyone got that one right, 40. Right, and then you just had to calculate, and I think it was 0.384 grams, right? Last one. Calculate the volume of water that must be added to 30 cubic centimeters of a 0.06 mole per cubic decimeter hydrochloric solution to dilute to. Okay, so it's dilution. Immediately, I'm going to start with this equation. Right. What do we start with? They ask us, calculate the water that must be added to 30. Okay, so the volume I start with is 30, and the concentration of the solution I start with, 0.06. Right. And then after the dilution, it should be a concentration of 0.04, and you work out the new volume. And if you get that, I hope most of you got 450 cubic centimeters, right? Is that the answer? No, that is not the answer. This is the whole new solution, right? They didn't ask what should be the new. They asked what must be added. So in the question, that was the most important thing. What must be added, right? So you already started off with 30. So end up with a final solution of 450. What you need to add will be, one more, 450 minus the 30 that was already in there. Yes? Am I working on different papers than yours? Sorry? V2? Is it just 45? I think I changed it from here. 45 minus 30. Just 45 minus the 30. Okay, so it's just 15 cubic centimeters. Right. But this is old stuff, right? The only one that's a little bit new is the concentration that is diluted. Are you happy with that one? Okay, so let's move on. Let's talk about why do we call some of the acids strong and why do we call some of them weak, and what does an acid do? Right, so the next table on your next page is sort of a summary of what's happening with acids and bases, right? Now, if you look at the acids, try and look at HCl, HNO3, H2SO4, and tell me, every atom there, every element there, hydrogen, is it a metal or a non-metal? Non-metal. Do you remember your periodic table, or do you have it next to you, right? You have to remember metals and non-metals, right? So if you look at all of them, you will see hydrogen, chloride, nitrogen, oxygen, sulfur, all of them being non-metals, right? And if non-metals bond together, what type of bond does it form? Covalent bond, right? It forms a covalent bond. What is a covalent bond? They're just sharing. They're just overlapping their orbitals and sharing, right? An ionic bond forms ions. This one is just sharing and overlapping. So there's no ions, right? So this one's got no ions at this stage. So if you react that with water, it now has to react with the water to produce ions. And if it has to produce ions, we say it ionizes, right? It has to produce ions. So you started off with something that don't have ions, and it's going to produce ions. So in this instance, the water should be in the equation. You have to add the water, right? Because it's reacting with the water. So all the acids start out covalent, right? And for all of them, you should add water because it has to react with the water. It has to ionize. Everyone happy? Right, let's move on. How about the base? What do you know about potassium? Metal or non-metal? Non-metal, right? And that is bonded onto oxygen and hydrogen, and they're both non-metal. So you have metal and non-metal, and that makes it an ionic bond, right? So all the strong bases, they are ionic, right? It means they already have ions. So for them, you're not going to put the water in the equation. Do you see, if you want to put water in, you put it below the arrow, right? And you can also put just a single arrow, that's fine, right? But it does not go into the equation because it's not going to react with water to make ions. The ions are already there in your crystal, right? So what's happening when you put that crystal into water? They just come loose, right? They dissociate, right? Do you know dissociate is the opposite of associate, right? I associate rain days and pancakes, right? They go together. So if you associate, you put them together. If you dissociate, you just take them apart, right? So because this was ionic, the ions was already there. They were present in the crystal. The only thing that happens, it is drifting apart. It's dissociating, right? And that's the first thing you have to know. Acids will always ionize, right? But when you get to bases, let's look just at strong bases. Strong bases will dissociate. We're still going to talk about ammonia, which is an exception to every rule, right? So you have the acids, and they are covalent, and you must put the water in because it's now going to react with the water. It's going to ionize. What is the difference between strong acids and weak acids? Now, if you look at the weak acids, non-metal, 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 all covalent, right? So for all of them, water will go into the equation, right? Right. So they now have to ionize. They now have to make ions, right? Okay. What happens to an acid? Well, Bronsted-Lowry, right? You always also have Arrhenius, but we're using more of the time Bronsted-Lowry. Bronsted-Lowry tells you it's a proton donor. So what will happen to the acid? It will donate a proton, an H+, right? So if that one gives off an H+, it should end up as Cl-. This one gains the H+, so it ends up H3O+, and that's the hydronium ion, right? That's the one that makes my solution acidic. So with acids, both strong and weak, they start out covalent. So they don't have ions. So you have to put water into your equation, and they will ionize. They will ionize. They will form ions, right? And one of the ions will definitely be the hydronium ion, because there's an H+ that is given to the water. So all the acids will ionize. Now, what is the difference between a strong acid and a weak acid? And that comes in the word completely, right? Strong acids ionize completely, weak acids ionize incompletely. Now, what does that mean? It means that if you put 1,000 hydrochloric acid molecules into the water, all 1,000 of that hydrochloric molecules, well, will go over. All 1,000 will form 1,000 of H3O plus molecules, right? So if I put 1,000 in, I get 1,000 hydronium ions out. But if something is a weak acid, it can give off an H plus, and then it will ionize. But what happens if I put 10,000 of them in there? 5 or 6 of them will end up ionizing and forming ions. So you will just have 5 or 6 of those, even though you put in 10,000, right? So it's an acid. It can give off H plus, but it's a weak acid. It really doesn't want to do it, right? So I put 10,000 in. How many do I get out? 5 or 6, right? So that is what's meant by incompletely. Not all the acid molecules will react. Only some of them will react. Right. Let's go on. So all the acids ionize. Strong ones ionize completely. Weak ones ionize incompletely. Now, if you want to, you don't have to. Up to matric, you don't have to. But if you want to, you can show the completely. By when you draw arrows, right, the forward reaction and the reverse reaction can happen. By drawing the forward reaction arrow bigger than the reverse reaction, we are saying it is strong, right? It will react more to that side. And with a weak one, you can put a small arrow to the back and a bigger one to the front, and that will tell you that only a small amount of the molecules will be doing that. So is there any way to look at the formula and say this is a strong one? No. You have to learn the first table, right? Then you will know these are the strong ones and they should react completely. So all the acids ionize. Weak ones, just incompletely, not all of them. Strong ones, completely. Right, let's go on to the next one. When you look at the bases, now we looked at those bases, and they dissociated completely. What does it mean? Every single molecule that I put in there will react, and they produce OH minus, because the water gives off the H plus, right? Or rather, the OH just dissociates. Weak base. Now, here is one. Whenever you see ammonia, right? Whenever you see ammonia, there must be bells and whistles going on. Because ammonia is always different from all the others. Can you see it doesn't have an OH, right? What do you know about nitrogen? Is nitrogen a metal or a non-metal? It's a non-metal. Hydrogen? Non-metal. So this is the only base on your table that is covalent. Right. It is the only base that is covalent, or from the ones that you have to learn. And if it's covalent, there's no ions, right? It needs to react with water. So for this one, you have to put the water in. For those, they already had ions. They just dissociated. We didn't put the water into the equation. But there's this one. That is covalent. There are no ions. You have to ionize. So this one, ionize. While all the other bases just dissociate. So if you learn the definitions, they will always say acids will always ionize. Right. But when you get to the bases, they say ionize or dissociate. Why do they say that? Most bases dissociate. But NH3, that will ionize. Do you understand the exception? Okay, so how do you write it? If it's an acid, you have to write the water in. You have to do a proton transfer, right, an H transfer, and you will end up with the hydronium ion, always with an acid, right? And whatever is left of your acid, the negative part. When you look at a base, if it's a strong base, right, it needs to react completely, but it does not react with the water. It just dissociates, drifts on top, sort of, Right. When you get to NH3, it is covalent, and for this one, it will ionize, and you need to add the water. Right. And a base, if it ionizes, it means it is receiving an H+, right? With an acid, it is giving off the H+. With a base, it is receiving H+, right? Okay, just to talk about strong and weak, just look together at the next question. A solution of the acid HX with concentration 0.15 moles per cube decimeter is prepared. The concentration of the hydronium ions in the solution is 3,2 times 10 to the minus 6. A. Write an equation for the reaction of HX with water. Right, try that one. See if you can write that equation. The reaction of HX, an acid, with water. The acid is a proton donor, right? So it will take the proton and donate it to the water. So you will end up with the X minus, right? And H2 and the H plus will give you the hydronium ion, right? So this is your reaction. And now in B, I'm asking you, is HX a strong acid or a weak acid? Now X is not something you know, right? This is just a hypothetical acid. But what they tell you is they made a solution of 0.15 moles per cube decimeter. Right. If it is a strong acid, it must ionize completely. Right. If it's strong, every single one that you put into water must give you an H. So if this was strong, how many H3O plus did you expect? 0.15. And what did they get? The concentration of the hydronium ions in their solution is only 3.2 times 10 to the minus 6. That is a lot less. So it tells you not every HX molecule ionized, only some of them ionized, right? And therefore, this is it a strong acid? No. The number of H3O, the concentration of the H3O that's produced is less than the HX that I put into water. It's less. And therefore, I know it ionized incompletely. And therefore, it is a weak acid. It's easy to learn the definition, to know a strong acid ionized completely, a weak acid ionized incompletely. It's when you start applying it, right? When they give me numbers and they ask me to understand, then it's a little bit more difficult. This one fine with you? Let's move on. Now, I've given you a long list, and this is the last thing we're going to do, right? We're going to write a lot of equations. And now you have to think, what am I doing? Is this a reaction with water? Then it must be ionization or dissociation. Or is this a reaction with a metal, reactive metal, metal oxide, the ones that we did on the first page? You have to distinguish. So let's look at the first one. The reaction between magnesium hydroxide and nitric acid. Magnesium hydroxide, Mg, OH, 2. Magnesium being 2 plus and hydroxide being minus 1. Added to nitric acid. No way around that. You had to learn your table. The table on the first page, it should be in your head. Now look at this one. What type of reaction do we have here? This is the acid. What is this? The OH will make it a base. And also from your table you know it's a base, right? It's a weak base. If a base and an acid react, what we call that type of reaction? You can say acid-base, but what's another name for it? Neutralization, right? Neutralization. So how does neutralization occur here? What should be the products? Salt and water. So you do an ionic exchange. The magnesium is going to bond onto the nitrate. What does magnesium nitrate look like? Magnesium is 2 plus. Nitrate, NO3 minus, is -1. So you need 2 nitrates for the 1 magnesium. And the other product should be water. And now we just need to balance it. 1 magnesium, 1 magnesium. Oxygen, 2 over there and 3 over there makes it 5. Here's already 6 and another one, 7. Definitely not right. Let's try the hydrogen first. If I put a 2 here, 2 hydrogen, 2 hydrogen. Now the oxygen, 2 and 6, making it 8. Right, and there, 6 and 1, 7. Not yet. Okay, hydrogen. 2 there, 2 there, 2 there, right? 2, 4, 4. 1 magnesium, 1 magnesium. 2 nitrates, 2 nitrates. Right. So that was the first one. The next one, and now you are going to write it on your own. The next one I'm asking you to write, and I am giving it to you very easy. I could have said just nitric acid in water, and you would have had to know nitric acid in water, what's going to do? It's going to ionize. So write the ionization of nitric acid. So you need nitric acid, you need water. This is a strong acid. Acid is something that will donate a proton. So you will end up with NO3 minus, right, in solution, and the hydronium ion. And you can say also in solution. And if you want to, you can indicate that it is a strong acid. How do I indicate that it's strong acid? Big arrow, small arrow. But if you prefer for grade 11 and 12, you can just put 1 arrow to the right, and that will also be fine. Next one, reaction of lithium hydroxide in water. Now you have to think, what is lithium hydroxide? What's going to happen when it reacts with water? And then you have to write the reaction. So go on from there. If you're finished with number C, just go on. Let's look at number C. Lithium hydroxide. Lithium being 1 plus, hydroxide being 1 minus, right? In water. What do I know about lithium hydroxide? It's a strong base, okay, a base, and it's metal and non-metal. It tells me it's already ionic. So for this one, don't put water in your equation. Just put water underneath the arrow. It's not going to react with water. The ions are already present. They're just going to go in separate directions. So you have your lithium plus going in one direction in the solution, and you will have the OH minus going in another way in the direction in the solution. So you have to know, this is a strong base. You have to know it's already in ionic form. I don't put water into the equation. On to the next one. Oxalic acid was one of the acids that we had two formulas for. If you chose to work with COOH2, right, then it would look like this: sodium oxide, sodium plus 1, oxide 2 minus. So sodium oxide should look like that. And now they bond. Now think about COOH. If that splits up, what will it give you? The H plus, that's going one way, right? And actually two of them. Remember the molecule? The H's on both sides will go. So you will end up with COO2, 2 minus, which is a strange one, right? On your table of ions that we used when we did moles, you have that table of ions. You will see that ion, right? What do we call, this is oxalic acid. What do we call the anion of oxalic acid? You can turn back. That was on page, let's just see. On page 14. I hope we corrected that one, right. Oxalate, oxalate. So if you have oxalic acid reacting, it will make something oxalate. So the oxalic acid, the negative part is oxalate. Right, go on with the next one. We just need the lamp and then we'll start again. Do the rest of that page. Right, let's start again with the oxalic acid. The oxalic acid is that one that we talked about that is organic, and you've got the two hydrogens on the opposite sides. So if it's going to react, it's going to give off both those. And then it ends up COO2, 2 minus. So it looks strange, the 2 and the 2 minus, but if you know what the molecule look like, then it's not that strange, right? So you have this one. And you have the H plus. And what's happening is the sodium that is positive is bonding to the negative part of the acid. So you will end up with sodium, and sodium is plus 1, and that COO2 is 2 negative, so you need 2 sodiums for that. And then you call that sodium oxalate. Sodium oxalate. And now what's the other product? Well, it's an acid, and this is a metal oxide, so the other product should be water. Let's balance. 2 sodium, 2 sodium, 2 oxalate over there, 2 hydrogen, and that looks nice. What if you prefer to write it H2C2O4, NO2O? Then you would have had Na2C2O4 and H2O. So it depends on which one you choose to use. If you choose to use the top one, then you must continue in that way. If you choose the bottom one, then the oxalate will look like that. So if you see this, it looks terrible, huh? It looks very, very difficult. But once you know that it comes from oxalic acid and it's just oxalate, sounds much the same, then it gets easier. Next one, ammonia with water. So go on, if you finished with number E, just continue with the rest.
teaspoons with hydrogen?
Because if you look at the molecule, it's equally. When you saw ammonia, I hope you remembered, oh, this is the exception to all the rules. What do you know about ammonia? Ammonia is a base, but it is a covalent base. Non-metal, non-metal. No ions there, it's covalent. So when the ammonia reacts with water, the ammonia is a base and it will receive an H+. It is a proton acceptor. And then you end up with NH4 in solution, and you will end up with OH- in solution as well. So this is the only base that you will put the water into the equation. Next one, reaction of sulfuric acid. Sulfuric acid, H2SO4, added to water. What do you know about sulfuric acid? It is a strong acid, right? I can indicate it with a big arrow to the right. It's a strong acid. What happens to an acid? It donates protons. Now, usually it only donates one and then the other one after the other. But it depends. If we are going to write the reaction, you can say it reacts with 2 water molecules, give off 2 H+, so it will end up SO4 2- in solution and 2 H3O+. So you get 2 hydronium ions for every sulfuric acid molecule that you put into water. So that makes it a strong acid, and also, what do we call it if it gives off 2 hydrogens? I hope some of you remember diprotic, right? 2 protons given, diprotic. It's a diprotic acid, so it gives all. Now, usually, if they ask you to write the equation, I will write that one, but there's sort of an exception. You actually have to think H2SO4, this is actually a 2-step reaction. First, it reacts with the first one to give HSO4-, and then what happens is that one reacts further. And it gives off another H+, and then you end up with SO4 2- plus H3O+. Now the question is, when should I write it as one reaction, and when should I write separate reactions? Now, whenever they're asking us about conjugated pairs, what do we know about a conjugated pair? They should only differ with one H+. So if they're asking conjugated pairs, I will write them the bottom one, because then it's easy to show the conjugated pairs. If they're not asking for conjugated pairs, we assume that it is going straight through, and we're just writing this one. So we assume it's going to produce 2 hydronium ions in the process. Right, next one, reaction of sodium carbonate. Sodium carbonate, sodium being plus and carbonate being 2-. And that reacts with hydrochloric acid. It is one of our grade 10 reactions. So if you're not sure, go back, check, and complete that one, and also balance. Right, so with this one, it needs to be a salt, and that will be the sodium chloride. And the other product, H2CO3, and it immediately splits up in H2O and CO2. So that's not something that you know, that's something you go back. If you don't know the grade 10 reactions, and you have to check, what does a carbonate give me when it reacts with acid? And then you have to balance. 2 sodiums on this side, we need 2 sodiums on that side, 1 carbon, 3 oxygen, right? 3 oxygen, 1 chloride, 2 chlorides. Okay, so we need another one there. So it's only that 2. Right, the next one, once again, I ask you, give me a neutralization reaction that gives potassium sulfate as product. So you want to produce K2SO4. If it is a neutralization, what is reacting with what? The acid and a base. And for a base, it's going to be a OH something. Should that be potassium hydroxide? And what acid? The sulfate comes from the acid, so the acid being H2SO4, because it's an ion exchange. The potassium takes the sulfide, and the other product should be water. And then we just need to balance it, so it's a 2 over here and a 2 over there. Just 3 more for you to do. With water, it will always be ionize or dissociate, right? And with the other things, you're back to the grade 10 equations. Can you just get the papers? Do we have one pair? Okay, it's just okay. Another one. How many pairs do we have? 4. I think there's 6. 5. 6. Can you just send it along to them? Right, oxalic acid. You can either choose COOH2 or H2C2O4. Choose which one you want to work with. All acids will ionize, so I need the water to be in the equation. It needs to react with the water in order to ionize. Is it weak or strong? Weak. I can show that with small and big arrows. Not necessary, but you may. And what's going to happen is H plus is being donated to the water. So you get COO to 2 minus, and it's giving off 2 hydrogens, so you have 2 waters there, and it will end up with 2 H3O plus. And you can add in solution. If you did this one, then it would be hydrogen going, and you will end up C2O42 minus, and you will end up with 2H3O plus. It is a weak acid, so how many hydronium ions do I expect? Not many, right? Only some of the molecules will react. The others will stay in this form. Preparation of sodium carbonate. I want to make sodium carbonate. Once again, neutralization. Tells you it must be an acid and a base. For the base being something OH, that will, OH being negative, it will be bonded to the sodium that is positive. Sodium hydroxide. The carbonate should come from the acid, so you've got H2CO3, carbonate acid, carbonic acid. And now they will react, and you will end up with that. And if it is a neutralization, the other product that I expect is water. And then we need to balance it. 2 over there, 2 over there, balanced. Last one, ammonia, NH3, and hydrochloric acid. Ammonia and hydrochloric acid. What do we need know about ammonia? It's always the exception on the rule, right? All the other bases that we work with, if you go back to the first page, all the other bases had OH, right? So they ended up with water as my extra product. But when you get to ammonia, ammonia always the exception to the rule. With ammonia, you don't get the water. With ammonia, the NH4 is a base. It accepts the H+, and if it accepts the H+, then you will end up with Cl- on this side. And this one will become NH4+. So it accepts a hydrogen ion, H+ from the HCl, and it becomes NH4+ in solution and Cl- in solution. So it's the one acid-base reaction that does not give you water as a product. So it's an exception on the rule. We want to go on with redox reactions, right, with electrochemistry. But just quickly look at my reactions here. When you look at them, can you tell me this first one, is that a redox reaction? Is that a redox reaction? Yes, that is a redox reaction. Because we're now going to look at redox reactions. And redox reactions has got electron transfer. There's electrons transferred from something to something. Now over here, the zinc is in a 0 state. It's just a zinc metal. And over there, it's in a compound. So now it's zinc 2+. It must have received electrons or donated, in this instance, donated electrons. So if it changed the charge from there to there, 0 charge to a +2 charge, we know that is a redox reaction. If you look at the second one, the H+ went to the OH-. No change in charge, right? And the zinc went to the chlorine. It's still zinc 2+. It was zinc 2+. It did not change. The chlorine used to be -1. It's still -1. It didn't change. So it's all about the charges. Now, did everyone receive that page with the electrochemistry? The guys at the back? Right. So we're going to look at redox reactions, a reaction that involves electron transfer. Now, you've done a lot of redox reactions. You maybe didn't just know that you are doing redox reactions. If you look at a nice reaction, say for instance, we take aluminium and we react aluminium with chlorine gas. What product can you get? Aluminium chloride. And that looks, aluminium being +3 and chloride being minus, aluminium, Cl3. Right, 3 minuses for the 3+. Everyone happy? Now, for this, we can balance it, and we call it balancing with inspection. You look at the left side, you look at the right side. The left side's got 1 aluminium. That's the same as on the right, 1 aluminium. But then you get to chlorine. Chlorine on the left side, 2. Chlorine on the right side, 3. So what do I have to do? It seems I have to make this more, but if I put there a 2, it's still not going to work. So it's 3 over there and 2 over there. And then I've also changed my aluminium. So this we call balance by inspection. We did that from grade 9. Look left, look like, decide. Now we're going to do this another way. Let's start with the aluminium. If you look at aluminium, it starts off with aluminium without a charge on this side. But on that side, it ends up as aluminium plus 3. So during this reaction, we had that change. How can an aluminium become an aluminium 3+? Is it giving off electrons? Is it receiving electrons? It's giving off electrons. And if you were not sure about that, the easiest way is to say charge cannot be removed from the system. So what you start with, you should have at the end. The total charge on the left side is 0. So what is the total charge on the right side? It should also be 0. So if you put your electrons on the wrong side, you will see that, because then the charge on the left and the right-hand side will not be the same. So aluminium is doing that. Now, it's good enough to say electrons are given off, but we have a nice, correct terminology to use. What do we call giving off electrons? I hope all of you talked about oxidation. Right? Oxidation. But what's important is this is not a whole reaction. This can't occur on its own. So we call it a half reaction. It's only half of a reaction. You don't have containers on the shelf where you can put the extras, or from where you can get some electrons when you need it. Right? What is produced must be used. And this one only produced. So it can never happen on its own. It can only happen if you have something else that will take that electrons. So this is the oxidation half reaction. Now, if you have to remember that, the English guys usually like to talk about oil rig. To remember, they say oxidation is the loss of electrons, and reduction is the gain of electrons, and that makes it easy to remember. So we are losing electrons, we have an oxidation half reaction. So just a small way to remember that. Let's go back to our reaction. Now we're looking at the chlorine. We start out with Cl2. Now I can't break that into separate chlorines, they are bonded together. If it's written down there, they're bonded together. And that ends up being Cl-. And I need 2 of them because there's 2 chlorine atoms on the side, I need 2 chlorine atoms on that side. So where should I put the electrons? Do I need to put the electrons on the left side or the right side? On the left side. So that the total charge on the left side is 2-, and the total charge on the right side also 2-. So the electron gained by the chlorine to become Cl-. This is one where electrons are gained. If I gain electrons, I'm working with reduction. So this is the reduction half reaction. Reduction half reaction. Right. Now, no containers where you can put the extras. So at the moment, I am producing 3, and I'm only using 2. Right. So if I'm producing 2, that won't work. What can I do to produce as much as I am using? I can do that one 2 times in the time that I do that one 3 times. So I'm going to take 2 aluminiums and make 2 of those, and twice 3 is 6. So I go and I do the whole reaction 2 times together. So it's 2 of those, 2 of those, 6 electrons. Right. And then, how about chlorine? The chlorine, I'm going to take 3 of the chlorine molecules that will use 6 electrons and give you 6 Cl minus. So now this one, we multiplied with 3. So the top one with 2 and the bottom one with 3. And now we're going to put them together. We are producing 6 electrons, we are using 6 electrons, now we're fine. Now reduction and oxidation, when they occur at the same time, we call them redox reactions, because it's reduction and oxidation, redox. And now it's a reaction. It's not a half reaction, because it will occur. The one is giving off and the one is receiving. So what do we end up with? We end up with 2 aluminium and 3 chlorine molecules, giving you 2 aluminium plus 3s and 6 plus 3 and 6 Cl minus. Now, if I want to, I can add those 2 together, so you will get 2 aluminium and 3 chlorine, giving you, if I put aluminium and chlorine together, it should be aluminium chloride like that, and I can make 2 of them because I've got 2 aluminiums and I've got 6 chlorine. And can you see we've once again balanced our equation. So that top one we balanced by inspection, just looking on the left side and the right hand side. And the bottom one we balanced by using half reactions. And that's something they can ask you. Balance something by using half reactions. Now, here I did not provide you with the half reactions. You had to write your own half reactions. You had to look at the bigger one and get your own half reactions. So, in this one, we have electrons giving off, right? Electrons are given off, so it is oxidation. But let's look at the charges. What's happening to the charges? Aluminium being a 0, and afterwards being plus 3. So what is happening to the charge over there? The charge is increasing. And it should be like that because the electrons that we remove are negative. So our substance should become more positive. What if we add electrons? Electrons are negative. If we add electrons, what's going to happen to that oxidation number? 0 over there, no charge. And over there it's minus. So the charge is decreasing, it's reducing. And this thing is reduction. So what we want to do in future, we don't always want to look at the electrons. We just want to look at the charge and say, oh, so this one, the charge is going bigger, it's oxidizing. Or the charge is going smaller, it is reducing. But now we have a problem. What happens when you have something like, say, for instance, NH3, that is a covalent bond because it's non-metal and non-metal. So there's no charges. So what are we going to do? Now, we just changed the word. Instead of charge, we are now going to work with oxidation numbers. If it's an ionic substance, it's the charge, right? But if it's a covalent substance, it's sort of what would have been the charge if this one was an ionic compound. So if you look on your very first page there, the first thing we're going to do is we are going to practice assigning that oxidation numbers. Now, if you have something and there's nothing written in the right-hand top corner, then this is a neutral substance. And all the charges, or in this instance, all the oxidation numbers should add up to give you 0. If it is a compound ion, then you will find the total charge there at the top, and all the oxidation numbers should add up to give that. Now let's start. There's a number of rules, right? The first rule, if it's a pure element, it takes 0. Pure element means it's not bonded to something else. So that can be something like sodium, right? Sodium not bonded to something else, that should take a 0. But it can also be something like Cl2. That is not bonded to another type of substance, it's pure. So that will also take a 0 as my oxidation number. Then there's a few rules. If you're looking at elements in compounds, bonded to something else, we're always going to take hydrogen as +1, oxygen as -2, right? There's a few exceptions, but there are so few we're going to ignore them to start with. Hydrogen, we're always going to take as +1. Oxygen, we're always going to take as -2. Anything that's in group 1 on the periodic table is +1. Anything in group 2 is +2. So let's start with this one. The question is, determine the oxidation number of the indicated elements in the following compounds. You have sulfuric acid, and now I'm asking you, what is the oxidation number of the sulfur? I can't ask the charge, it's not ionic, so I'm asking what is the oxidation number. Now, when you do this, the easiest way is to, at the top, write the oxidation for one atom. And then at the bottom, put them for all together. Put them all together, because you use them all together to see that you get to 0. So for this one, I will say hydrogen in a compound. Hydrogen in a compound will always take +1, right? So hydrogen being a +1. But I have 2 hydrogens. So if there's 2 hydrogens together, they will be +2. Oxygen, go back. Elements in compounds. Oxygen will always take a -2. So that oxygen is in the -2 state, and 4 of them together will give me -8. And now, what should the sulfur be for them all together to give you 0? That sulfur should be a +6. So the oxidation number of sulfur in H2SO4 is +6. Is that something that you expect of sulfur? What do you expect of sulfur? If I asked you what is the charge of sulfur, what would you have told me? -2. Now, to understand that, let's go back to the periodic table. If you look at the periodic table, where do you find sulfur? Sulfur in group 6. It's got 16 electrons, because it's got 16 protons. If it's neutral, 16 electrons. Where do you find that? Now, you don't have to be able to draw this anymore, but do you remember about 1s and 2s and 2p, right? 3s, 3p. So if it's got 16 electrons, it was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Right. So the first level is filled. The second level is filled. How about the third level? The third level has got 6 electrons that we call valence electrons, right? Now, for it to get into a stable state, it needs to be like a noble gas. So it needs a full outer energy level. What is the easiest way for sulfur to get a full outer energy level? The easiest way would be to go to someone else and ask them to give them 2 electrons. So if you add 2 electrons there, then for those 2 extra negatives, your sulfur will be a sulfur, that is sulfur -2. So yes, that happens, and then we call it sulfide. But sometimes it takes the long route. Sometimes instead of getting 2 more, what can it do? It can take all 6 in the outer energy level and give them away. Instead of getting 2 more, it's going to give away all 6 in the outer energy level. So then, if it's given off all those, it will become a sulfur, and now it is sulfur +6, because it gave off 6 electrons. There's 6 protons that will not be cancelled out. So what does sulfur +6 mean? It tells me this one's got noble gas structure, but it went the long way around. It gave off 6 instead of just gaining 2. And then, so sulfur can sometimes be 0, when it's not bonded to something. It can become sulfur -2 when it gets 2 more, right? And it also can become sulfur +6, but then sulfur does something unexpected, +4. How can sulfur become a +4? Now, if you look at the outer energy level, don't look at those that we borrowed, just look at the 6. Can you see 2 of them is in the s orbital? It's a sub-level. And the other 4 are in a p level. So if it can't give off all 6 to get a noble gas structure, to get a full outer energy level, then it gives off the 4 in the p orbital and becomes s +4, and then at least it's got a sub-level that is filled. So that's not a whole level, that's just a sub-level. So what does that tell me? A sulfur that's +4 is most likely going to be a little bit reactive, because it's not really got a full outer level, it's just got a sub-level that's filled. It's got an S level that's filled, not a whole energy level. Right, how about chlorine? Chlorine, you find in group 7, right. So for chlorine, what do we expect? We expect chlorine to be -1. So sometimes you get chlorine that's not -1. Let's look at one example on your page. We'll do the others just now, but just skip to HOCl down there. Hydrogen is a +1. Oxygen is a -2. So what can you tell me about that chlorine? The only way for this to get 0 is for that chlorine to be a +1. Is that something we expected? No. The moment that this happens, that chlorine +1 is a very distressed chlorine. It actually needs an electron to become a noble gas, and now someone has removed one of its electrons. So if you have something on Earth that is really looking to get electrons somewhere, that will be a Cl+1, right? It needs electrons. It wants to take up, it wants to gain electrons. It wants to reduce, right? It wants to reduce. And if it wants to reduce, then this is a very good oxidizing agent. It's something that you add to oxidize something else. So if you get chlorine, usually it's -1 because that's the short route to noble gas. But you can't get +1. But then this chlorine will be very reactive. When you put this HOCl, right, you can get it as sodium hypochlorite, or you can get it as calcium hypochlorite. If you put it into your swimming pool, that chlorine that's +1, what's it going to do in the swimming pool? It's looking for electrons, right? It's moving about looking for electrons. So where can it find electrons? It takes it from the algae. And then the algae die, and you have a nice clean swimming pool, right? If you add that distressed chlorine to your washing, what's going to happen? It's looking for electrons. Where is it going to find that electron? From all the colors, right? All the color molecules, right? All the pigments. And it's going to say, give me these electrons. And if it takes the electrons, what's happening to the color pigment? It's going to fall to pieces, and then you will have nice whitewashing, right? Night washing. So if you add jig, you are adding chlorine in a highly distressed form, and it's going to take electrons from that. So the oxidation number is not just something, it tells you what is the state of this atom. Is it in a reactive state or is it not? Right. So let's continue with that one. We did the sulfur. Let's look at the next one. You've got lead oxide. Lead oxide. Now, if you look at this one, the oxide, PbO2, oxide being -2, 2 of them together to give you -4. So what is the oxidation number of that lead? That lead must be a +4. The lead must be +4. Go on. Iron oxide. If you look at this iron, oxygen being a -2, 3 oxygen together be -6. So the 2 ions together should be plus 6. So what is the oxidation number for one ion? One ion should be plus 3. Next one, dichromate, and we're looking at the chrome. Dichromate, and we're looking at the chrome. Now tell me, what do you know about potassium? Potassium is in group 1, and for group 1 we take plus 1. So together they are plus 2. Oxygen is minus 2, so together they are minus 14. So what do I need? I need a plus 12. But there's 2 chrome ions. So 2 chrome atoms, what will everyone be? So every single chrome will be a plus 6. So 1 chrome plus 6. SO4 2 minus. SO4 2 minus. What does the 2 minus tell you? That all the oxidation numbers together should give you a minus 2 answer. So if every oxygen is a minus 2, that will give you minus 8. But you have to end up with 2 of those minuses as your answer. So this one should be plus 6. So there you have sulfur in the plus 6 state. What does it tell you about the sulfur? It gave off the outer 6. It's got noble gas structure. Right. Next one. We looked at SO2. Now we're going to look at FeCr2O7. Now this looked like a problem because I know the oxygen, right? I know the oxygen is minus 2. That gives you minus 14. But I don't know the chrome, and they're not asking the chrome. They're asking the iron. So here we need something. We need your knowledge of the ionic table. Go back to your ionic table and tell me the whole dichromate altogether. What is the charge of a whole dichromate? It's minus 2. So what should the charge of the ion be? Plus 2. So sometimes that is the way to go, to use your knowledge of the ions. So you have to know that table by heart. Next one, vanadium pentoxide, V2O5. And I'm asking you for the oxidation number of the vanadium. Every oxygen is minus 2 together, that is minus 10. So the 2 vanadiums should be plus 10. So every vanadium plus 5. Yes, I can hear a lot of perfect answers over there. Right. Now, on the right side, there's a few more. Just continue on the right side to do all the examples on this side. Right, let's start from that top one. Hydrogen always takes +1. Chlorine, right, is the one I'm looking for. Oxygen, -2. So over here, I already have -6, and there I have +1. What am I missing? +5. So that chlorine should be a +5. Right, looking at the next one. I don't know iron and I don't know sulfur. So I've got a problem. Now I think about my ionic table. What do you know about SO3? Sulfite. I hope you know your periodic table. If you look at the sulfite altogether that should be -2. So that gives you that the iron is in the +2 state. And then you look at them separate. Forget about them all together. And now say, okay, so the iron being +2, every oxygen is a -2, so that is -6. So I've got -2 there, I've got +2, -6. So what do I need? +4, +4. So that sulfur is in the +4. So this was a difficult one. You had to use both methods. You had to use the iron table method to get to the charge of the iron, right? And then you had to take them separately in order to get the sulfur. Should I do this one again, or are you happy? Happy? Not happy? Okay, let me do it again. Let's look at this one. FeSO3. Now, I know the rule tells me oxygen is -2, that is -6. But I have a problem. They're asking for the sulfur, and I don't know iron. Why don't I know iron? Iron can be either 2+ or 3+. It's one of the transition metals. So I don't know this, and I don't know this. So what can I do? Now you think of your table of ions. What do I know about a sulfate altogether? SO3 is always -2. And that tells me that iron atom should be a +2. So now I think about them separately. Iron is +2. Oxygen is -2. So this part is -6. That part is +2. What do I need? I need a +4. So that is the oxidation of that sulfur. Let's move on. So that one was +4. SO2, easy. Every oxygen is -2. Together they are -4, and that sulfur should be +4. What did you do with HNO3? Well, oxygen and hydrogen is known, so I can just do HNO3. Hydrogen takes 1, so this part is +1. Oxygen takes -2. This is -6. What do I need? Altogether they must be 0. I need a +5. So my N is in the +5 state. And for nitrogen, that would mean giving off everything in its outer level. So that nitrogen +5. We're going on. Sodium sulfate. Sodium sulfate. Sodium sulfate. Now, sodium is easy because it's in group 1. We have a rule for group 1 things. If it's in group 1, it takes +1, so that is +2. The oxygen being -2, that takes -6. So we are up to -4. And that tells me that sulfur should be a +4. Sulfur +4. That chlorine we already did. This carbon one, copper one, quickly. You don't know C and you don't know copper. So what do? We think about the carbonate altogether. Altogether, the carbonate would have been -2. So the copper should be +2. Right, so now we know the oxidation numbers and we have to apply it. So if you take the next page, let me see if I can find that one. Yes. At the top we have the oxidation and reduction. Just quickly, one example. If you take this equation, copper starts out on its own. So there is a pure substance. So over there, the charge or the oxidation number is 0. And on the other side, it's bonded to a sulfate. And a sulfate, you know, is a -2. So that copper is a +2. So what's happening to the copper? The copper is going from 0 to +2. So the oxidation number is increasing. The oxidation number is increasing. And that tells you that the copper is the one that is oxidizing. And that makes it the reducing agent. It makes it possible for the other thing to reduce. If you look at H2SO4, H is +1, there's 2 of them, oxygen -2, so that gives you -8, and then that ends up with the sulfur being +6. So you work out +6 on this side, and then you go to the other side, and you work out that sulfur, and now it's +4. So what happened? +6 to +4, the oxidation number reduced, and therefore we say H2SO4, and we say all together H2SO4 is reducing. You don't say the sulfur reduces, right? The sulfur would not have been +6 if it was not bonded to the other things. So it is the whole thing that is going to be reducing. So let's apply this to the first one. Hydrogen, if it's on its own, what is the oxidation number? 0. Chlorine on its own? 0. Hydrogen in a bond, +1. Chlorine, well, it's bonded to a +1, so it should be -1. Right. Let's look at hydrogen. It goes from 0 to +1. 0 to +1 is an increase. It tells me H2O is oxidizing, and that will make it the reducing agent. If you look at chlorine, it starts out 0, it ends up as -1. What happened to the oxidation number? It reduced. So we say chlorine reduced, and it is the oxidation agent. Next one, sodium. On its own, what is the oxidation number? 0. Hydrogen in a bond, that will be a +1. Oxygen in a bond, that will be a -2. So afterwards, the sodium is in a compound. It's group 1, so it will be +1. Oxygen, once again, -2. Hydrogen, once again, +1. And how about that hydrogen? What is the oxidation of that hydrogen? 0. Nice one. So the sodium is going from 0 to +1. It's increasing. So this one is the one that is oxidizing. This one is the reducing agent, because the oxidation number is increasing. Now, we have hydrogen and we have oxygen. If you look at oxygen, over here it's in a bond, so it's -2. Over there, it's also in a bond, so it's also -2. So that oxygen didn't change. Let's look at the hydrogen. It started out as +1, and over there it's also +1, so that was not a change. But over there, it is 0. So if you're looking at the hydrogen from here to there, it went from a +1 to a 0 state. So what happened to the oxidation number? It reduced, telling you that water is the substance that is being reduced. Water is the substance that acts as my oxidation agent. And one more, zinc. Zinc on its own, oxidation number 0. Now, copper bonded to 2 chlorides. Now, chlorine is not one of those that we know, right? But you know your ionic table. When chloride is not bonded to something else, the chloride is a -1. So you've got 2 -1s, so that copper is a +2. Over to the other side. The chlorides both being negative, the zinc will be +2. Copper on its own, 0. So if you look at the zinc, it's going from 0 to +2. It's increasing. So zinc is oxidizing. Zinc is my reducing agent. If I look at the copper, it's starting out as +2. It's ending up as 0. So what's happening to the oxidation number? It's reducing, telling me that copper chloride is reducing, and therefore it is my oxidizing agent. Right, last one. NH3. Every hydrogen being a +1, altogether being +3. And therefore the nitrogen will be -3. Go over to the other side. Oxygen not bonded to anything. So that should be a 0. Over to this side. Oxygen -2. So that nitrogen should be, nitrogen here, +2. Hydrogen in a bond +1, oxygen in a bond -2. So let's look at the nitrogen. It was -3 on this side and it went to +2 on that side. So what happened to the nitrogen? -3 +2, it increased. So NH3 oxidized, and it is my reducing agent. Right. How about oxygen? It's going from 0 on this side, and it doesn't matter if you look to there or to there. It's going from 0 to -2, so it is reducing. So oxygen is reducing, and it is the oxidizing agent. Right, it is the oxidizing agent. So they're going to ask you to identify the oxidizing agent, and this is what you do. So when you look from left to right, you look at one atom and one atom's oxidation number and one oxidation number on the other side. Not to the totals, right? One on the left, one on the right, and that will give it to you. Right. Now, on the very first day, we did not do the very last question. Do you remember I told you go and look at the very last question? I just want to quickly look at that answer so that you can mark it if you've done that. It was on page, what was that? Page 13. Page 13. Right, we had this question where they said the two crates with apples are being pulled up an inclined surface with a constant force F. The inclined surface is at an angle of 30 degrees with the Earth. Well, they draw it in, so I don't have to go and write it down. Crates A and B have masses 6 and 4. That is also in my picture, so I don't have to rewrite. Both crates have kinetic friction of 0,2. So for both of them, the kinetic friction is 0,2. Then the last thing, the crate accelerates from, so it is starting of 2 meters per second, so that was my initial velocity, and it went to 2.5, so that was my final velocity, over a distance of 4 meters, so they also gave you delta x. And then the first question was, are these crates in equilibrium? And the answer was no. Right, equilibrium means F net is 0. It will mean you are with Newton's first law. So you're either standing still or traveling at constant velocity. And this is not constant velocity, the velocity is changing. Right, so there is no net force, and I know that because this crate is accelerating. If it accelerates, then there is a net force, and it's not F net 0. Right, then they asked us, draw the labeled force diagrams. Right, now for force diagrams, you should actually have blocks there, and I draw a free body diagram, so this is not totally correct. Okay, but the important thing is you have to have every single force correct. If you had one force missing in your picture, then the answer could not have been correct. Right. So the first thing is go and draw gravity, but put the separate components for gravity, right? And then think about what is taking this crate up. It's being taken up by F, the applied force. What is keeping it back? Why isn't it traveling faster? We already know gravity's perpendicular compound is keeping it down. What's also keeping it down? This rope, the tension in the rope. If it was not pulling the other one along, then it would have been faster. So the tension in the rope is also pulling back, and you also have friction keeping it back. So if you don't have all the forces on your force diagram, you won't have all the marks, right? Go on to the next one. This one. What is pulling it up? Only the rope. Remember that applied force is acting on that one, not on this one, right? It's pulling that one up, and that one is pulling this one with a rope. So on this one, don't put F there. F is not working on this one. F is working on the top one. So what's pulling it up is just the rope. That's the only force pulling it up. That tension you can think of, it's part of the applied force. And then there's the friction keeping it down, and also the component of gravity. And then they ask you, use equations of motion to calculate the magnitude of the acceleration. I hope everyone got that very easy, right? That was just choose the correct one, substitute. I hope everyone had that. Right. And then they're asking us, calculate the magnitude of the tension in the rope. Can I see how many of you, okay, first, how many of you did this? And did you get the 41,26? I hope. Right. Now, if you looked at the two, they are now asking for the tension in the rope. It might be necessary to do simultaneous equations, but sometimes it's not. So how am I going to start? I'm going to start by saying, I'm going to start with this one. Because that one, they are asking T, and I also don't know the applied F. So I'd rather start with this one, where I know all the forces except the tension in the rope. So let's work with the bottom one. So if you work with the bottom one, it's accelerating, therefore I know I have to start with F net equals m times a. That's Newton's second law, right? So I have to start there. If I have to start there, now I'm looking not in the perpendicular direction, I'm looking at the movement, right? So I'm looking in the direction of movement. So upward is my positive direction. So T will be my positive one, right? And if you look at that one, T being the positive one, and in the downward direction, what's pulling in the negative direction is your parallel component of gravity and also the friction, right? So let's quickly go and calculate the friction. Now for that, you had to use your equation, and you had to know that the normal force is equal to the perpendicular component, and you had to know for the perpendicular component you have to use cos. So that was just to get the frictional force. And for then, we use the frictional force over here, and you have to have the parallel component, which is sine of the whole gravity. Right. And then you end up with that one. So we only use the bottom one. It was not necessarily for simultaneous equations. They like to ask you things that are different from the hundreds that your textbook give you to practice. If it's always two and you have to get simultaneous equations, then when you get in the test and it's only one, you are sort of baffled. Right. So it should not always be necessary to do both. Let's see if I can refocus and give it to you a little bit clearer even. Right. So then you get the value for T. And now in the next questions, you can use that value for T. So let's now go on. Now they're asking us to calculate the magnitude of the applied force. If I'm looking at the applied force, now I'm going to work with the top one. So now I'm going to work with the top one. It is still accelerating, so for the top one, we're still going to say F net is m times a, right? And let's look at which forces. You've got the applied force in the upward direction, that would be a positive. And what's keeping it back? The parallel component and the friction and the tension in the rope. So in the positive direction, you have your applied force, you have the tension in the rope pulling it down, you have gravity parallel pulling it down, you have friction pulling it down, and that is m times a. Right. And we're working with a 4 kilogram mass, and we already have a. So it's a question of substitution. And then you still have to calculate the kinetic friction. in order to put it in there. Yes. Sorry? Oh, is the answer there incorrect? Okay. Just change that. Okay. Okay. So you were working towards the wrong answer. Okay. Did you get the right answer? Oh, perfect. Nice. Right, everyone, very last thing today is I want to give you my email address, right? You can write to me at sarita@swanepoel.net, and I would really appreciate it if in your email you just tell me you grade 12 JuniorTukkie, that I know where we met each other and what we did. Right. And then you can also ask your questions. Remember, I might not be able to answer today or tomorrow. Maybe it's next week, but I will try. Right. So you can send me that. Can I just quickly ask, which topic was the best one for you? Which did you learn the most from? Newton? For who was Newton the best one? Right. Who learned the most from moles? Mole calculations. Okay, so that was a good one. Right, and then acids and bases? Right. And redox, electrochemistry? Okay, so today's work was fine. Right, I hope to see you next year at the grade 12 JuniorTukkies. Right.